I should have been a business major.
No. No. That's silly too.
Okay. So it seems like we have a decent amount of people in here right now, so I might as well just go ahead and start this up. Let me see. Okay. And oh wait, what am I doing? Can you guys see this? Can you guys see the presentation
Yep.
right now?
Yes.
Okay.
Yeah, we can see
Yeah. Yes.
All right. So today's lecture is just a general overview on processing. But before we really get into that, we do have an announcement next Monday, November 2nd. Of course, this is our off week, usually for the this is usually our off week for lectures, but instead we're going to be talking about an Arduino project that the executive board has been working on. Recently, Dr. Gila met with Micron, and they basically told him that while they like to see the stuff coming out of SCRO right now, they want us to work on a certain type of projects, which is putting sensors on machines and basically capturing data from those machines and basically trying to optimize parameters using that data that you gather from these Arduinos. So currently, our rough idea that we came up with on a different day was trying to optimize basically the parameters to make a cup of coffee. So try to make as consistent of a cup of coffee using Arduino and like capturing temperature data and things like that. But next week is going to be us talking more in depth about what Micron told us and all that sort of information, and then possibly brainstorming to see if there are other projects we should work on either in addition or instead. But now moving on to the actual lecture portion. So these are the things that we're going to cover, just generally speaking. There's crystal growth, oxide growth, photolithography, and deposition. So we will just jump straight into it. So this is the general life cycle of the process of producing a device. So you go from SAN to purified ingot, slice the wafer, process the wafer, and then take the dye from the wafer. And it's separated into those 4 general categories up above. So we're going to start out with material preparation. So in the semiconductor industry, we really want to try to have a single crystal, which is the far left, the monocrystalline structure. It basically just indicates that the crystal lattice throughout the entire structure is uniform versus polycrystalline and amorphous. Because as you can see in a polycrystalline structure, you have these divisions where they're uniform in these small patches, but other than that, like there are these points where these uniform patches are colliding at certain locations where they meet other crystals that are in a different orientation, and where they meet are called grain boundaries, and they cause inconsistencies in the energy there. And then amorphous amorphous is very similar, except it's essentially just completely random. There's no organization to it, and it causes the properties not to be isotropic. So whenever we're looking for semiconductor grade silicon, we're looking for single crystal or monocrystalline. So the way that we grow these silicon ingots are I had to look up, as you can see, how to pronounce this. I still don't remember how to announce this. It's the Czochralski process. Probably butchered that. But it's performed in an inert atmosphere, usually argon, as most processes where you don't want anything reacting. Argon is usually the go-to gas because it's relatively cheap and it's inert. But it's it's basically creating a uniform seed crystal. Okay, I'm getting flustered here. So you take a uniform seed crystal, as you can see in this picture. You have the seed crystal right here, and it's dipped into a crucible of melted silicon, and then it is slowly extracted, and that seed crystal spins, and that's how you get this nice circular shape. And so it's basically almost similar. It's kind of analogous to, if you're familiar with it, SLA printing, where you have the source, it dips into a molten material or a liquid material, and then as it pulls out, it hardens and creates a new layer. So this entire new crystal that's being grown on top of the seed crystal, it is all one singular crystal. It's that monocrystalline structure that we're looking for from our silicon. And the reason why it's rotating is just to make sure you have that uniform circular shape. And so while there are often impurities in the melt in the liquid silicon down at the bottom, usually the impurities tend to want to be segregated into the liquid portions rather than the solid portions. So the crystal that you actually grow is actually very pure, and so it's usually 99.999% pure or something along those lines. And so that's how you get these ingots over here. And so when you move on, then it gets grinded down to make sure that the wafers are perfectly round. And then from there, they get sliced using a wire saw into the wafers that we actually manufacture. And then a lot of times, they won't be perfectly round. They might actually have a flat edge to them that gets cut at the bottom, basically so that you know the orientation of the wafer and it makes alignment easier. So thermal oxidation, you grow an oxide layer on the substrate, which is what is that's the silicon portion of the wafer. So the higher the temperature, usually the faster the oxidation and the thicker the layer. But the purpose of this layer is mostly for so that when impurities come into contact with the wafer, because everything can be an impurity in device manufacturing. It prevents those those unwanted impurities from diffusing into the substrate. Rather, it diffuses into the oxide layer, and it insulates the substrate from metallization pattern and the gate in FET devices. So usually when you grow an oxide layer, since it's the oxygen and the air a lot of the times reacting with the silicone, you have this oxide layer actually growing into the substrate. So you have 55% of the substrate above where the silicon wafer actually begins, and then you have about 45% growth into the silicon surface. And there's two types of way to grow oxide. I mean, technically, there's three. You can do a deposition of sorts, but the two common ones are wet oxide and dry oxide. So in wet oxide, the silicon actually reacts with water in the atmosphere. So you vaporize water, and it's in the furnace, and this water vapor is in the furnace, and so it reacts with the water to generate hydrogen gas and silicon dioxide on the surface, and uh, and then those are used to usually grow thicker field oxide layers, but it's slower, it's high quality, and it's porous. Dry oxide, it just reacts with normal oxygen. It's silicon plus oxygen, which produces the SiO2. It's usually better for growing thinner layers, and then it generates faster and lower quality non-porous oxide layers. The other important thing is that when it says Si plus O2, it's not just atmosphere. We're not just generating it with the atmosphere. We're pumping in excess O2 to also catalyze the reaction and make sure that it's getting a steady stream of oxygen to it. The next step from there would be photolithography, which is heavily dependent on photoresist. So photoresist is what's actually used to pattern the features onto the wafer. It's a light sensitive polymer. There's two different types. There's negative PR that hardens when it's exposed, and then there's positive PR where it hardens where it's not exposed. Uh, for the summer processing lab, if you were doing the MOSCAP lab, as you probably know, we were using negative photoresist. So basically what happens is that it's a liquid polymer. So you have these chains of polymers that are basically scattered at random, and then when it's exposed to light, it begins to cross-link. So there begins to become where they were once just long chains of non-associated polymers. They start to connect to one another and creates a cross-linking structure, and it begins to harden together. Um, and then we can move on. So the way that we deposit photoresist is through spin coating. So you have this vacuum pump that you attach to the wafer, or that you rest the wafer on, and it spins up to a certain angular velocity that you have to determine based off how thick you want your photoresist to be, and depending on the photoresist and the viscosity, there will be different curves to show how fast you should have it for a certain thickness. Um, so you dispense it either before you start spinning or after you start spinning, depending on what you want. You can either have a static or a dynamic spin, which is either you can either start the spinning after you've already deposited the photoresist and ramp it up to a high speed from once when it's deposited, or you can have it at a lower speed, deposit it, and then accelerate it up to a higher speed once when the photoresist is on there. And that should give you this relatively uniform film of photoresist, which then you can take off, bake for a little bit, and then it will be prepared for exposure. So now moving on to the photomask. The photomask has a pattern that will have UV light shine through it and onto the photoresist layer, and depending on which parts are exposed or not and what type of photoresist you have will depend on what sort of pattern you get out of the photoresist. So as you can see, we have some example pictures of dyes here. The photomask that we have the in the teaching lab, it is for a full wafer, and in that you have all of the different devices you can possibly have as separate little sections like this. Ours are circular rather than being rectangular like this. But there are also some photomasks where there will be one photomask on a die, or there will be one die on a photomask, and then it will be magnified into one small area, which is called, I believe, stepper. It will come up in the later slide. It's called stepper lighting. It's right here. So we have parallel light exposure, which is the image that's on the photomask is a 1-to-1 ratio to what is projected onto the PR and what is projected onto the substrate. Then you have stepper exposure, where the size of the photomask is actually larger than what is being projected onto the PR, and through some lenses, it focuses all of the light onto a small area, and it basically does it one die at a time, or it's laser written, or the entire pattern is laser written onto the wafer. And then there's also optical proximity correction, which is essentially just trying to account for um, diffusion of the light through these sections. And so it's kind of just meant to make all of the what areas of the mass are exposed more uniform throughout the shape. So we have these little squares on the edges to make sure that it fills out the entire image that we want and account for diffraction. And so this is kind of just a practical example from the summer lab. So we have this little shape up here that we call the rocket ship. And just because the photomask that we had it wasn't perfect. So rather than getting these separate ovals like this that was actually on the photomask, we were getting images like this where they all kind of blended together, which in the end doesn't really matter, because what these are called are fiducials, and they're essentially just alignment marks, so that when you're applying a second layer of photoresist, you know where to line it up on your mask. to essentially make sure when you deposit metal onto it, the metal is going on the right places. So this is just a diagram of everything up to this point. So you have the substrate, you have the passivation layer, then you apply photoresist, you apply light to the photoresist, and in this case it is negative or no, this is actually positive photoresist. Um, then it's uh, then it's developed, which essentially moves all of the non-hardened photoresist. And then from there, you can go to etching, which will then go through the oxide layer, which we will now discuss. So you can either have wet etching or dry etching. Wet etching is a chemical etching. It's usually some form of hydrofluoric acid. It usually has an etch rate of around 2 micrometers per second. Or no, what was the etch rate of the BOE, Colin? It was how fast?
It was relatively slow. I think it was around 5 nanometers a minute or something like that. 6. I don't know.
Either way, it's a very controlled reaction rather than pure hydrofluoric acid, which would probably just go straight through the silicon dioxide layer. It actually is a very controlled reaction where you can time it using a normal stopwatch and be able to get pretty consistent precision with what you're looking for. So you can look at the thickness of your oxide layer, and you can basically say we want this this many nanometers off of that thickness, and just basically using some simple math, you can kind of determine basically how long you need to have it in this buffered solution before you need to take it out. But so um, the solution we use is called buffer oxide etch, and it's just a diluted hydrofluoric acid solution. The buffer allows the solution to stay neutralized, and it affects everything isotropically, which means that basically it affects whatever it's attacking, it attacks equally in all directions, which is why rather than um, just burrowing straight down through the silicon dioxide, it burrows down into the side, which is how you get what are called these little undercuts, where there will actually be missing silicon dioxide from below the PR, and you can see that in some of your microscopy. Dry etching actually uses plasma. It unlike the BOE, it's actually anisotropic, where whatever um, it won't it will just attack in one direction. It will just attract straight down from the first exposed area of the silicon dioxide straight down to the substrate. It uses high energy plasma to etch the exposed material rather than a chemical method. We usually don't use that in the lab. We usually use it more for cleaning up the wafers prior to depositing metal, just to make sure that there's no contamination on the wafer. But it is generally speaking, it's the more effective method at doing this. But there are in some cases points where you do want to have it can be considered beneficial to have undercutting. BOE, as mentioned before, it's a diluted solution of hydrofluoric acid, and that buffer that we talked about is actually ammonium fluoride. So it actually can, since it has a free not ammonium fluorine ion, um, it actually it contributes fluorine ions to the solution, and it helps to keep the solution neutral and control the etch rate, because rather than wanting to react with hydrofluoric acid, there or rather than allowing the hydrofluoric acid to dissociate and break up into hydrogen and fluorine, there are already fluorine atoms in the solution, which helps to control the rate because it keeps the hydrofluoric acid from dissociating like it usually does, which helps to prevent the hydrogens from reacting with the hydrogen and the fluorine from reacting with the silicon. So it increases the iso ice. Oh my! I'm so sorry. It increases the isotropy of the etch compared to the concentrated hydrofluoric acid, and it more easily etches more porous materials. So it kind of just demonstrates it in this image below. There's so you have your layer of photoresist, and then there's an opening in between, and then you have your layer of silicon dioxide, and then you have your silicon substrate. And what it will actually do is it will come down here. It will go in between the PR because you have this opening in between the PR from where the unexposed PR was developed away, and it will come down here and it will etch away the silicon dioxide, but leave the bare silicon since it's non-reactive with it. And then we come to doping, which is ion implantation, where essentially you have an ion source, and it'll basically generate these ions, usually of phosphorus or boron, and it will basically turn them into ions, and then because they are they're no longer neutral, they'll be accelerated by this magnetic field and actually just accelerated into the substrate, and it propels them into interstitial sites, which is essentially, if you imagine just like a square of 4 atoms, you have this little opening in the middle. It'll just propel these ions into that little space in between the four atoms, and it will remove silicon atoms from the crystal lattice structure, and that's how we get N-type and P-type doping. And then it kind of demonstrates that in this picture. So it launches these ions into the substrate, or yeah, and then you have all these displaced atoms. But what we can do is we can slowly heat it up and anneal them. And when we get above a recrystallization temperature, all of these atoms will begin to settle back into their original crystal lattice, with now these new ions taking the place of silicon atoms in the crystal lattice, which will eventually it'll basically allow those atoms to contribute or take away excess electrons and contribute to the electron mobility or the hole mobility in the device itself. So moving on now, we go to deposition. So there are two general types of thin film deposition, which is usually what we use for the metal deposition to actually create contact points. We have chemical and physical deposition, and so you have this little chart over on the left. Physical vapor deposition and sputtering are the two I'm going to talk about today, and then I'm just going to talk about general chemical vapor deposition because while it is important, we can eventually go deeper into that when we have uh, our more in-depth discussion on thin film deposition. So chemical vapor deposition is basically where gaseous chemicals are flowed over the surface of a wafer to cause a thin film of material to be deposited on the surface of the wafer. It it produces very flat surfaces, filling gaps and covering height differences. And as you probably saw on this slide, epitaxy is considered a form of thin film deposition, and that's actually how a lot of more complex wafers are being produced now, or they're doing research into how they're being produced. I know that a lot of companies are looking into making making the epitaxy of gallium arsenide more applicable to produce gallium arsenide substrates. Um, and it's just a very it's an interesting method of depositing material, and a thin gate oxide or silicon nitride is deposited via CVD to act as an insulator between the gate and the silicon. And now we can move on to PVD. Um, or this is sputtering. This is just physical deposition still. Uh, it's a type of sputtering is a type of physical deposition, and so basically plasma. It can either be done in an electric field or a non-electric field. But so you have this plasma that ionizes a target metal, and basically it'll free these atoms now, that are now ionized, and you'll have this inert gas that'll flow, and it will basically direct these new ions onto a surface, and it will begin to coat all of the it'll begin to coat your substrate in whatever ions you're freeing. So you can see down here that you have your, in this case it's aluminum. You have aluminum up here that is being ionized, and you're producing Al plus atoms and electrons, and then all these new aluminum ions are now being directed onto your substrate by an electric field and also by an inert gas. So, and this can be done for conductive or non-conductive materials, but it just depends on the methodology of whether or not they are conductive. Um, in this case, we're talking about aluminum, so in this case it is conductive, so usually it's performed in an electric field of some sort. Then moving on to evaporative deposition, it uses electrical resistance to heat a sample in a vacuum. So you have this tungsten boat in a vacuum chamber, and then you actually have all of your wafers loaded upside down into this rotating platform, and you fill your target material that you want to actually coat your substrate, um, loaded in either in beads or some other form. And then as you pass a current through that tungsten boat, it begins to heat up. And since the vacuum is so low, it's usually around 10 to the -6 or 10 to the -7 torr. It greatly lowers the melting point of anything. So those metal samples that are sitting in the tungsten boat begin to heat up and boil and evaporate, and this metal vapor begins to be deposited in layers uh, via this method. But the limitation of this is that it's essentially dependent on everything having a direct open path, which can be a little bit difficult considering that you need to have some method of actually attaching the wafer to it, which usually can be done via vacuum. But if in our case in the teaching lab, um, we were using smaller wafers than the machine was designed for, so we had some way to clip it on, which ended up have requiring us to cover some corner of the wafer with with a bended piece of metal, and obviously that prevents that area from getting covered by these released ion, or not ions, but these metal vapors. And then the last thing is that there would also be a step called chemical mechanical planarization. Um, Basically, you would have this slurry of chemicals that would be applied to the surface of the wafer, and you would have this rotating, almost similar to a file. Um, that obviously it wouldn't be that rough because you're trying to keep it smooth and undamaged, but it would just rotate and file down any inconsistencies in the surface, and it would just remove bumps and any features on the wafer that would be undesirable, or would possibly lead to failure or any sort of issues with the device. And so I added some of these extra resources at the end here. These are some of the links I looked at while researching this. So I have some links on the, I'm not going to try to pronounce that again, thermal oxidation, photolithography. I highlighted this link specifically because it's a really good resource. You guys can see this, right?
Yeah, we can see it.
Okay. So basically, this is a website for a company called Microchemicals. They provide us with our photoresist that we use in the lab, and I actually found this website. But it basically has just a bunch of essentially SOPs, SOP kind of not SOP sort of situation. And it gives you a lot of very useful information. Kind of like, let me see. Wet etching of silicon, and it will tell you basically. Uh, I'd used this document before, so I know. Like it tells you about etch rates of silicon, what BOE is, and how does it work. And so there's a lot of very helpful resources there, and I just wanted to highlight that just in case if you were curious about wafer production, anything about photoresist or lithography. It's a great resource considering that this is what they do. This is like their entire business model. They also have a lithography troubleshooting guide. Basically, just has like example pictures of like or like just like it just gives you like basically information as to like what could have gone wrong in your process if you're getting a certain outcome, and it's just helpful little stuff like that. um, and then I also have some resources on BOE, which is the document that I showed you from microchemicals, doping, specifically ion implantation, and then some information about sputtering deposition and evaporative deposition. Other than that, I'm done here. So does anyone have any questions? Okay. Other than that, thank you guys for coming. I really appreciate it. Thank you so much. And you guys are good to go. Oh wait, wait. Oh, the Arduino workshop is going to be on, we're going to be having our first meeting next Monday. So it will be the same time, it'll be the same time on Zoom as a normal GBM. It will just be on one of our weeks where we usually wouldn't have a GBM. So I'll send out the link to that at some point within the next week or so. I'll probably just send the Zoom link itself on the day of, but I will create a an event probably after this. I'll be sure to make an announcement after this about we actually are trying to make sure that you guys don't need to provide anything. Um we're trying to we're actually going to try to put some of SCRO's funds to make Arduino kits to try to send them out to you guys to make sure everyone has the same equipment. So it's just going to be when we actually get to start working on the project, we're going to try to have you guys work in groups because that is something else that companies want to know that you're doing is working in groups. And especially right now where communication isn't necessarily the easiest thing, it's a decent challenge to have to do all of this online. But we think it would be a good learning opportunity for you guys. So we're going to try to have a couple meetings before you guys actually start working on anything, and that will give us time to actually refine the plan as to what we want to do for the actual project itself, how we're going to run it, and then sorry about that, and then getting you guys into groups so that you guys can actually start communicating, start working on stuff like this, and you guys will actually submit a budget and a list of items you want to send to or you want us to give you, and we'll put in the order for it, and we'll try to make kits for everybody to make sure everybody has a similar starting point essentially. No problem. Yeah, but for next week's meeting in particular, you don't need anything specific. Or like you don't need to have anything ready, is what I'm trying to say for next week. No problem. Any other questions? I think no, no one else asked a question. Anyone else? I am seeing the people who are saying that they need to do the thing for baby circuits. I'll get around to all of you after this. Just um, if you really want to make sure I remember, please just send me a DM through the group me, and I'll get to that at some point. Thanks. Right, no problem.